Hey guys, today we're going to introduce series circuits and how to do math when it comes to series circuits. So remember, series circuits are circuits that only have a single path of travel for the electrons. That means there is only one choice of where they can go. Every time you add a resistor, it becomes increasingly difficult for the electron to travel. What that means is every time you plug something in or add a light bulb, it's harder for the electrons to travel through that circuit because it's more stuff to go through. In order to determine the characteristics, we must simplify the circuit. And in order to do that, we have to calculate the resistance if only one resistor was present. So like I said, there is one path of travel. Every electron must go through the same path. So when we see these resistors, we have to treat them a specific way. Equivalent resistance is the total resistance present in a circuit. It is the total number of ohms that a resistor would have to have in order to replace all of the resistors in the circuit. So if there are 5 resistors, how many ohms must one resistor have to replace all 5? In series circuits, we calculate this by simply adding up all of the resistors. So this equation, Req is the equivalent resistance, is equal to R1 plus R2 plus R3 plus all of the resistors until we get to the last one. So this Rn just means that we can add 7, we can add 20, we can add 3. It doesn't matter. Due to Ohm's law, which is V equals I times R, as the resistance increases, the current must decrease. Since the voltage is staying the same, we're providing the electrons with the same amount of energy. If they have to drop off that energy at multiple locations, they're going to be traveling at a much slower rate. Okay? And we're going to look at this in the next slide. So here we have a circuit, and we're going to calculate some unknowns for this circuit. We have a single battery, and this battery is providing 60 volts of energy to those electrons. We have one resistor that is 17 ohms, a second resistor that is 12, and a third resistor that is 11. So when I add these up, my Req is R1 plus R2 plus R3. So my Req is 17 plus 12 plus 11, which is equal to 40 ohms. So I'm going to plug 40 into this table right here to make it nice and neat. I'm going to use V equals IR for this next step. So V is 60 across the battery. If my Req, or my equivalent resistance, is 40, I would have 60 equals I times 40. Divide it by 40, and I is equal to 1.5 amps. So I'm going to write that here. Now, since each electron only has one path of travel, and they can only move as fast as the electron in front of it, every single location in this circuit has the same current. So I'm going to rewrite 1.5 in all 3 of those boxes. It has to have 1.5 amps at the 17, at the 12, and at the 11, because there is only one path of travel. Now, this middle box, the voltage drop across the first resistor. I'm going to again use this V equals IR equation, but I have the individual resistance of that first item and the current traveling through it. So I'm going to multiply those together. I am losing 25.5 volts of energy to this first resistor. My electrons are dropping off 25.5 volts and then continuing on. 12 times 1.5 is 18. At this second resistor, my electrons are dropping off an additional 18 volts of energy. And 11 times 1.5 is 16.5. At this last resistor, my electrons are dropping off 16.5 volts of energy. So I've given away all of the energy from the battery at this point, and these electrons are being forced back to the beginning, and then they're going to travel through a second time. So here are some things I want you to star. Star number 1. Your voltages must add up to the voltage at the battery. 25.5, 18, and 16.5 added together is equal to 60. Second star, your currents must all be the same. Since there's only one path of travel, they only have one option, each of these values must be the same number. Okay? So we're going to do one more practice problem together before I set you loose and have you do it on your own. So this new practice problem, we have an 11 ohm, a 6 ohm, and a 5 ohm resistor. So our Req is 11 plus 6 plus 5, which is 22 ohms. So 22 is going to go in my Req box. I'm going to use V equals IR. V is 12, I is my question mark, and R is 22. I'm going to divide both sides by 22, and I, with rounding, is 0.54. So 0.54 is going to go here. Now again, since there is only one path of travel, every single electron has to travel through the same steps. My current has to be the same at every location. But those electrons will drop off different amounts of energy at each location. So I'm going to go back to this V equals IR to solve for the voltage drop at the 11 ohm resistor. 11 times 0.54 is 5.94. At the 6 ohm resistor, 6 times 0.54 is 3.24. And at the 5 ohm resistor, 5 times 0.54 is 2.7. Now if I double check, these should all be the same. These should add up to 12. 5.94 plus 3.24 plus 2.7 is 11.88. That's just because we rounded this number here. If we would have taken out a couple more decimal places, we would have had 12 exactly. But that's close enough for me. Okay, so in class we're going to look at series circuits, we're going to look at resistance and current, and then we're going to calculate some things like in this table. So I'll see you then so we can practice.